In part 4 of our lesson on verifying trig identities, you will learn how to verify trig identities by working both sides. In this method, you will work both sides of the identity independently of each other, turning them both into something new that equals each other. As before, you will line up the equal signs, and then you will use the properties and identities to work each side on its own. And remember, this is not an algebra problem, so you cannot do the same thing to both sides. You have to work each side independently. It's just that both sides will turn into the same thing, and then you'll know that you've proven the identity. So let's look at this first example where we have to verify the identity here. You can see that both sides are very similar to each other, and hopefully your first instinct is to factor each side. So let's look at the left-hand side first. We see that we can factor out a secant squared of t, and we would have left secant squared of t minus 1. Now here we know that we can use a trig identity and substitute in tangent squared of t. We bring down the secant squared of t. And maybe at this point we're not really sure what to do, so this is a good time to move over to the other side of the identity and work on that side independently. So similarly to the left-hand side, we can factor out, in this case, a tangent squared of t, and we would have left tangent squared of t plus 1. Here, we can use a trig identity and substitute in secant squared of t for the tangent squared t plus 1, and then we'll bring down the tangent squared t. And now you can see that both sides of the identity have been changed into something new that equals each other. So because of that, this identity has been verified. So we can say, therefore, verified. So once again, we had to work on each side independently of the other side, factor, do a trig substitution, then we went over to the other side, factored, and did a trig substitution until both sides equaled something new that was the same on both sides. In this example, we have to verify the identity, and we can see that both sides are pretty involved. Often when we see that, we're going to lean towards this method where we work on both sides and see if we can simplify them both into something that equals each other. It doesn't matter which side you start on. I might be tempted to start working on this right-hand side just because I know I can turn it into sines and cosines and see where that begins to take me. We line up our equal signs. We know that secant of theta is 1 over the cosine of theta plus tangent of theta gets replaced with sine theta over cosine theta. In the denominator, this secant also gets replaced with 1 over cosine theta, and then minus a tangent theta, which is sine theta over cosine theta. Well, this is a nice development because all of these have cosine in the denominator, So when we clear out our complex fraction here, we're going to multiply by our LCD over itself. So we have cosine theta over cosine theta. Now in the numerator, we need to distribute that cosine theta times 1 over cosine theta becomes 1 plus cosine theta times sine theta over cosine theta becomes sine of theta. In the denominator, we're going to get cosine theta times 1 over cosine theta is 1 minus cosine theta times sine theta over cosine theta becomes sine theta. Now at this point, you might not be exactly sure where to go from here, so that's a good time to look over to the left-hand side and start to work that side. One of the things you need to recognize is that the numerator is a perfect square trinomial. I have a reminder for you right here, and this will factor into being 1 plus sine of theta quantity squared. And if we check it, we get 1 squared is 1, double the product, you would get 2 sine of theta, and then square the last term, you get the sine squared. Now in the denominator we have this cosine squared of theta, and when you look on the right hand side you see you have a 1 minus sine theta over here. In fact, the right hand side has all sines, no cosines. So I might be tempted to do the Pythagorean substitution here, where I can trade cosine squared of theta for 1 minus sine squared theta. Now nothing here will cancel, but we can factor this denominator. So let's take a look at that. The numerator will stay the same, 1 plus sine of theta squared. In the denominator, we will get 1 plus sine of theta times 1 minus sine of theta in our factoring. And now we see that we can cancel this factor with one of these, and the left-hand side becomes 1 plus sine of theta divided by 1 minus sine of theta, which exactly matches the right-hand side. You don't need to write it again, just draw the arrow down, and you can say, therefore, verified. So just a quick reminder that you have to work each side independently. So we started with the right-hand side and worked on simplifying it as far as we could. Then we switched over, went to the left-hand side, did some factoring, found out we could cancel one of the factors, reduced it, and it became something new, which equaled the new right-hand side. To verify the identity in this next example, I would probably be tempted to start with this right-hand side and change it into sines and cosines. We know that secant squared of x will become 1 over the cosine squared of x minus, we have a 2, this secant of x, of course, will be 1 over cosine of x. Tangent of x, we know, is sine of x over the cosine of x. plus we have this tangent squared on the end, which will become sine squared of x over cosine squared of x. Now, this has a denominator of cosine squared. Now look carefully at this one. This really is a denominator of cosine squared because it's cosine times cosine. And this has a denominator of cosine squared. So they all have cosine squared in the denominator, which means we can combine them. The numerator will be 1 minus 2 times the sine of x plus the sine squared of x. And here again, you want to notice that the numerator is a perfect square trinomial in this form, which means it will factor to be 1 minus sine of x quantity squared. And in the denominator, we have a cosine squared of x. Now, we could work on this cosine squared of x and try to change it into sines, or since we just did that in a problem recently, I'm going to show you how you could now work the left-hand side into the right-hand side that we have here. Now remember that one of the things that we can always do is multiply by 1. So we're going to take the left-hand side, which is 1 minus sine of x over 1 plus sine of x, and we will multiply by 1 in the form of 1 minus sine of x over itself. Now the reason that I'm choosing to do that is because I look at the right-hand side and I notice that I have a 1 minus sine of x squared, and I had a 1 minus sine of x here, so all I need is another one to end up with it being squared. So let's go ahead and write that numerator. We have the quantity 1 minus sine of x is being squared. Now in the denominator, we have 1 minus sine of x times 1 plus sine of x, which is 1 minus sine squared x, which we know we can use a Pythagorean identity to turn that denominator into cosine squared of x, and the numerator will stay the same. Now the left-hand side and the right-hand side are the same, so therefore we have verified this identity. In this example, we're once again being asked to verify the identity. Now we can see this is a pretty involved identity, lots of stuff going on. So it might be that our instinct is to change everything into sines and cosines, get common denominators wherever we can, do some simplification, see where it takes us. So maybe I'll start on this right-hand side. We know that cotangent theta is cosine theta divided by sine theta. We know we have to add to that. Secant theta is 1 over the cosine of theta times cosecant theta, which is 1 over the sine of theta. Our common denominator here, this already has a sine and this has a sine. This has a cosine in it. This one's missing that cosine. So if we multiply by 1, in the form of cosine theta over cosine theta to get that common denominator, then the right-hand side is going to become cosine squared theta plus 1 divided by sine theta cosine theta. Now you might be tempted to think that this is one of our Pythagorean identities, but it definitely is not. There's no direct substitution for cosine squared theta plus 1. So maybe at this point I decide to just stop here for a second. I may continue on doing something else, but right now I'm not sure. So now I think I will go after this left-hand side. Tangent of theta is sine theta over cosine theta. And that's in the numerator, and we have 1 plus cosine theta in the denominator, plus sine of theta over 1 minus cosine theta. Those are both already in terms of sine and cosine. Here we have a complex fraction. We're going to want to clear it out by multiplying by 1 in the form of cosine theta over cosine theta. So this first rational expression, the cosine here in the numerator will cancel this cosine here, so we're left with sine theta in the numerator, and in the denominator we have cosine of theta times 1 plus cosine of theta, plus this sine theta over 1 minus cosine of theta. Now here we want to add two rational expressions whose denominators are completely different from each other. So we're going to use this algebra rule here. We know that our new denominator is going to be the product of the two denominators that we have. So we have cosine theta times 1 plus cosine theta times 1 minus cosine theta. The numerator is going to be the sum of the cross products. So we're going to take sine theta times 1 minus cosine theta plus we have to take sine theta here times cosine theta 1 plus cosine theta. In the next step, we're going to need to distribute out this numerator. So this thing's getting huge. Let's see what we have here. Sine of theta times 1, we get sine of theta minus sine theta times cosine theta then we have this plus sign. Now we have to distribute sine theta cosine theta times 1 plus we have sine theta cosine theta times cosine theta. So we're going to get sine theta cosine squared theta, and our denominator is unchanged. Cosine theta times 1 plus cosine theta times 1 minus cosine theta. At this point, we may have chosen to want to multiply these together and get 1 minus cosine squared, But the reason I'm leaving them factored is because I'm not sure if I'm going to get to a place where I can cancel something. Until I get to that place, I want to leave everything factored here to see what happens in the numerator. In this numerator now, we have a minus sine theta cosine theta and a plus sine theta cosine theta. So those two are going to cancel each other out. We can see there's a sine theta here and there's a plus sine theta cosine squared theta. So I'm going to factor out a sine theta from both of these, and we will have left 1 from this, then plus cosine squared theta from this one, our denominator cosine of theta, and okay, I can see we actually will want to trade this out for 1 minus cosine squared theta. And the reason I want to do that is once I had this sine of theta in the numerator, I see that I want this to turn into sine squared theta so that I can do a canceling. So now we have sine theta in the numerator, 1 plus cosine squared theta over, in the denominator we have cosine of theta, and we'll do a trig substitution here where that becomes sine squared theta. Now the sine here will cancel one of these down here, and we get 1 plus cosine squared of theta over cosine theta sine theta, which is exactly what we had on the right-hand side. So that will come on down. Therefore, this has been verified.